All right. Good morning, everybody. My name is Jun Fukuoka. I'm from Japan, um, and I would really thank you for the organizer of these meetings, and also Dr. Altis, who's actually a really good friend for many years, to invite me to give this opportunity. I feel honored to have this opportunity to talk in front of those audience at the Swedish Society of Pathology, and I hope that my talk would be nicely accepted to the audience. Okay, so my talk, which I was asked to give to have from the Dr. Otis, was about the AI and pulmonary pathology, and summarize the area. And today's talk is mostly from our work. So, but I also implement some of the very important papers in it. But understand that most of the talks are actually they're coming from my own research and my own groups. So here's some disclosures. So today's my talk. I prepared those four topics. So first one is digital pathology and deep learnings. And the second one is using deep learning in practice. And third one is standardized diagnosis and the creation of the AI. And at last, I will talk a little bit about explainable AI models, what we are working on. So let's begin with some talks regarding the digital pathology and deep learning 101, which is very basic of the deep learning. Before entering to the AI, we definitely have to talk a little bit about the digital pathology because this is an entrance when you really want to start your work with AI. You need to implement digital pathology in your workflow. And I will show you what we are doing these days, especially for the lung field. We use actually the 100% digital for our diagnosis, and most of our network hospitals are actually using digital sign out. But I'll stick to the lung pathology for this time. For I want to introduce those three things. One is a crowd communication system for digital pathology and DICOM system. And also the second is creation of a consultation portal. And the third one is a nationwide web multidisciplinary discussion teams we created inside Japan. So creation of a crowd-based diagnostic system for lung cases, we use a crowd system named the past presenter. So how do we do is we just put all of those cases, and which is good about is not only a H&E slide, which of course we can do some of those annotations like this, and also not only H&E, we can also look at those spatial staining and immunostaining on the same page. And good thing is about is that we can also see those clinical data on the same page along with the DICOM data. So the quality is not that really great for the DICOM data, but we can still see those structures, everything. And by using this, we making the daily practice, and we connect to the diagnosis system of our university, and everybody hooked in using the username passwords, and make reports. And using these systems, we also created the consultation portal for the lung diseases, especially the focus on the diffuse lung disease. This is not only from our university, that it's under the umbrella of the Japanese Society of Respiratory Society. And the PI is actually from the other university, Nagoya University. I'm in charge of taking care of the pathology. We implemented all the modalities to the one portals. So we call this as a promise project. So how do we do that? So we're gonna log in under the username and password. Today I get the 4 cases, and I hit the cases. This one shows clinical data and also laboratory tests and every radiology and pulmonary function test. And also this connects to the patient's DICOM data. Although the speed is not that very fast, but the quality is really good. Its diagnostic level of the DICOM data is available along with the follow-up. And also, we hit the reporting system, which gives us the diagnosis of the clinician and radiologist. And sorry for Japanese language, but when we hit that, we can directly jump to the diagnostic system of the pathology. And if we hit the link, we can see the pathology and H&E and also the elastic fungus stainings to make a diagnosis. And after looking at that, we go back to the synoptic reporting system to make the report for the interstitial lung disease or diffuse lung disease. And if we hit this confirm, the patterns, then it will directly go back to the report to the contributors. And what is good about now is that all the pathology cases are coming to us in Nagasaki, and we scan and uploaded to the cloud system. And there are right now the 13 MDD teams inside Japan, and they are regularly working on those cases, which was central review from the older institute, more than 300 institute nationwide inside Japan. And every week we have a couple of times of the MDD web conference meetings between the pulmonologists, radiologists, pathologists, sometimes resident and AI engineers. And we also proved that these MDD system improved the original diagnosis and predict a better survival, which was published in ERJ a couple of years ago. So this is a kind of a basis how we use an AI, from now on. So by doing this, we have all the data in hand. Now we are creating AI to implement in this system. So before jumping to the AI, the clinical workflow, definitely they need to have some the workflow under the digital conditions. So let's move on to the AI 101. And I would start, about the very basis of the AI structures. Sometimes the people are not so, clear about the word deep learning. Deep learning is actually one part of the artificial intelligence. Artificial intelligence have actually a lot of things. Like, let's say automatic doors already artificial intelligence of some sort. And among the machine learning, there is one model called deep learning. And I'll talk about what the deep learning means in a minute. So this deep learning is actually neurons, which is not really a neuron, but simulating the human neurons. When some numbers are coming from the other neurons as an input, then it did the calculation by the formula. It usually has a filter in it. And then based on those calculations, output the numbers and connect to the next neuron. This is the basis. So this what we call the single neuron in human is actually called as perceptron in a machine learning word. And we just, like a human simulating the human brain, we connect all the neurons. Sometimes you can skip the sum of the connection to each neurons. Sometimes you have a recurrent route to go back to the sum of the neuron. You can design any way you want, but you make those networks and finally give some of the answers. So to do so, as you can imagine, older images actually, once this was digitalized, and then all of those actually the accumulation of pixels, right? So images should be translated to the matrices. So those matrices are actually, we are usually using our RGB. So let's separate those R and G and B. Just look at this G. And as you can see, those G's are actually all of those numbers, which is depending on the intensity of each the color. So how do we really extract the feature from these matrices? is that, so all of those numbers, we use those calculation formula, which is named kernel, actually, a filter. And we put this filter onto these images, and we will do the calculation one by one to get some, some numbers. So from the 9 pixels, we have one number, the numbers, and move one by one to get all of those accumulated numbers. So how do we extract the features? Right now, you see here, this is having a high number in a vertical manner. Here's all 0. This one is all minus. Means this filter is actually trying to extract the feature in a direction of the vertical the axis. So as you can see, vertical lines are actually highlighted. In this way, image with highlighted vertical features are extracted. If you go back, oops, so this is vertical. And if we do the filters with the horizontal directions, like you can see here, sorry, so this one is actually having a direction of the horizontal filter number, and then you can extract the horizontal features. Similar thing is for the diagonal filter. And by doing this, we can extract many features in different directions. So each of those features filters are called kernel. And then by having those numbers of those kernels filters, and then we would try to extract those features and connect to the diagnosis. This is actually not really right. This is just to simplify and let you understand more in an easy way. I just, created up some of the terms, translated to the word which we can understand. But it's actually not the reality. So what is good about this deep learning system is that the machine is actually the formula, the computer automatically identified features to classify whatever you want. But the features it's actually inside is actually the black box. And all of those are I created up, but usually contents are not be seen. So those are all invisible. That's why we call those as a black box. So that's the very basis of the AI. So by having that, what we can do, of course, we can have like, let's say, answer of the cancer versus non-cancer, adeno versus squamous, benign versus malignant, or information versus the non-information, or whatever. Each organ you can separate. Those we call classification. We just classify something. And also, we can do many more things. Of course, we can calculate the intensity of the, let's say, then count the numbers of the Ki positive things. Those are the very easy thing to do. I want to introduce one of the very important paper to the audience, which is published a couple of years ago in Nature Medicine. Go back. First, what they do was to make a classification model to separate lung cancer into adenocarcinoma and squamous cell carcinoma. As you can see, those are the judgment for each patches, and they just create the model to reach to the classification. Look at this AUC curve; they are pretty good. And what is oh, I'm sorry. What is the very unique about this is that, sorry, there's some contaminations. What is unique about this model was that at the year of the 2018, which is published in Nature Medicine, they try to predict the mutations, driver mutations from H&E only. And this was the kind of the strong breakthrough in this field. And this is a very famous paper, and many deep learning model papers actually referring using this paper as a reference. And as you can see, the ROC curve is not really great, But this gives us an impression, okay, we can see many different things, what we cannot do from our eye visions. So these are the models give us the kind of the impression that the machine learning can be useful for something we cannot do. Mm. I also want to introduce some of the, sorry about this. I also want to introduce another paper, which is not really in the lung field. It's in the GI tract the tumors, but they also did a similar approach like a previous case, and they used the images and data from the TCGA, as many the engineers doing, and try to predict the microsatellite instability inside the tumors. And this paper is also a key paper, coming from my friend, Dr. Faisal Mohammed at the MGH. And they just recently published this paper in Nature. What they did was this: they create the model to predict what is the original origin of the cancer to the CAP, which is the cancers of unknown primary. And this was actually that uploaded to the preprint paper almost a year ago, and now made it to the Nature this May. So it's a very recent paper. I would recommend you to read this paper. And okay, so next things is actually the deep learning model in practice. Let me just go back once again to the start over, because this one is, yeah. So here, deep learning model in practice. I'll show you what is the network of my group. I am located in this here, the university, Nagasaki University, but also I cross a point to the chair of the department in this one of the largest hospital in Japan, located in the east edge of the Japan. So having the distance of the 1,000 kilometers. So we have several the hospitals in a group. And how we do is that we create the AI model in Nagasaki University and centralize, and all of those institutes are connected through the VPN, and our AI team is analyzing all the cases and get the result, and then we all analyze those at the sign-off sessions. I'll show you the workflow in more in details. So before the diagnosis, all the tissues are digitized, and the when pathologists look at the cases, they give, of course, the diagnosis along with those ROI, where those the implement AI analysis would be requested. And then that our the AI teams in the university will download the cases and analyze using the AI models. And right after that, every morning we have a sign-off session, and our pathologists in many different institutes put it together to look at all those data and implement to the pathology report by using the data. And if the AI model is counting a tumor cell, the percentage, and if the tumor cells are enough to submit to the molecular analysis, we will submit the cases to the molecular test. So that's how we do. So this is read by the medical student, undergraduate. But how we do is that we pathologists put it together and just give an impression of how much the tumor percentage is. And we look at those, the data from the AI and think, that make a judgment if the AI is good enough to use the number, or, why does the impression is different? We evaluate. And afterward, if we need a modification to these numbers, we would modify. Like, let's say if the model has only identified half of the tumor cell, we have to double the numbers. By doing so, that we will just try to get the closest number to the reality and make a report. So this was actually published to this paper, so you can read this paper. I want to ask you the collaboration to predict the tumor cell percentage. If you have a smartphone, you can just scan this barcode to the join to answer what's the tumor percentages. If you don't have a barcode, I just sent a link to this page, Google Form, through the chat of this the Zoom, so you can connect to the Zoom, and then that you can answer to this model. So I will show you the video. So here's this the TBNA sample. And we don't count red blood cell because red blood cell doesn't have a nuclear. We just only need the number of the nuclei. So just count all the cells with the nuclear and predict how much is the tumor cell amount inside this tissue. Okay, so let's see if some people are kind enough to join this trial or not. Okay, let's wait a little bit. Please, oh, thank you for, so I will just start over this video once again. Yes, thank you so much for joining. You're very kind. So here is, do not count the red blood cell. Please just count the tumor cell. Okay. Thank you. Right now that okay, several pathologists are kind enough to answer to this the questions. All right, so I think we got the. I will finish this. Okay, so now what we got is. Just wait some seconds. Okay. Okay. So here's the result, what we got from today. So the many people kindly joined to this. So right now the 13 responses. It looks like the 15 percentage of the pathologists answered the 1 to 5, and the 6 to 10 was 15%, and also similar number, 50% was 11 to 15, and 16 to 20 is 7.7, and the 26 to 30 is here, and above 30 is also here and here. So quite a lot of the people are above 30. And I give you the answer. This tumor number was all counted, and the number was actually 14%. And this is, as you can see, that this is not the what we feel, as a fun work, right? We are not designed to count a cell every day. And there's no question that the machine does better work for this cell counting. So my impression is just do this type of chores to the machine learning, and we as a pathologist do a little more the joyful more meaningful the work, so which is a judgment of the AI to implement to the better the report. Okay, so we counted, we plotted those numbers prospectively for the first 50 cases, and this is the data. And as you can see, not many dots are actually on the line, and the dots are actually shifted to the left upper the area. Means here's this axis is the pathologist's first impression. This is a final reported number. Meaning that many of the cases are actually overestimated by the pathologist. And interesting thing was, it's not only that we can adjust our impressions. We also learn from AI. Interesting thing was, if I cut our judgment by the number 30, and that the average was actually closest to zero is actually ground truth. So closest to ground truth. But we learn somehow that we are overestimated by our experiences of the 30 cases. But afterward, what happened was that we don't improve anymore. So we have several variability, and then our prediction is even now we did like 200 more cases from that day, but we don't improve actually much. So I think that there's a limitation as a pathologist to how to say to do this type of work. So for next things I want to talk about is standardization of the diagnosis and the creation of AI. What do you mean? I would say, yeah, we would say we are expecting to have a many different AI popping up from the many startup, many companies, that we have no doubt about it. But then that which one we have to trust, or which one we have to select. Then the question touches to the okay, who educate this AI, or how this AI was created? What was the ground truth? That's the question. So ground truth. This is the ground truth to create the model is actually a very important message to the pathologist, as a factor to select the model. Because as everybody knows, the pathology has many gray zones, right? And in terms of agreement, varies depending on the field. And the correlation to relevant clinical data such as survival, recurrence rate, etc. Maybe these are the needed to really prove that that is a very good the model. And diagnosis given by an authority, brand name, Mr., professor, expert, blah blah blah. Or for me, it's like, let's say Professor Colby is my ex-mentor. If he created the AI, okay, wow, that's supposed to be wonderful, something like that. But then that many authorships are just coming up, popping up. Okay, which one we have to prove? The trust. How do you the select those models? Actually, the issue. And the consensus between expert pathologists may be good, but consensus, is this really the right answer? Sometimes big mouth would decide the consensus, and is that really a good way to do that? We're not sure. So we may need other statistics depending on the disease. So how do you define the ground truth? Very important things. Authorities' opinion, or consensus, or prognostic value, or pathologist annotations. So let's look at the pathologist annotation. Here, look at this, just the one of the cases. To shortcut the time, I just, make a time-lapse video. But as you can see, for this particular area, some people, like it's probably me, annotated the cancer. But I would believe that many people disagree to my annotations. Hey, look at this. These, arrowed cells are cancer to some of the pathologists. But some of the pathologists said, no, 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 no. They are stromal cell, look similar to the cancer cell, but they're maybe different. Or maybe they're maybe um, interrupt the pneumocyte, whatever, or just exaggerated endothelial cells. So it's very difficult to make a judgment without immunostaining. And I gotta tell you, if even with immunostaining, you gotta be stuck. It's not perfect at all. We are not in the once again, we are not in the place to make judgment for each cell. We are the person who make a diagnosis and think about the patient's benefits and stuff. So it's a different the work as we do. So then that annotation is not really a good way to make a good ground truth. One of the example, this is from the very old study we did, like let's say almost 10 years, more than 10 years ago. I pass along these 20 cases to the 29 very well-known pathologists of the lung disease, interstitial lung disease, and the red color is a UIP, and the blue color is a NSIP. All the other colors are different disease, and then a zero actually gray is an unclassifiable IIP. So look at this, it's a mess. None of the cases have a complete agreement, and when you look at the kappa barrier, it was awful. And even after the guideline, actually that was the reason why they upgrade the guideline and to make a criteria. But even with a criteria, when I did this inter-observer variation with Dr. Hastako, my fellow, did the nice work to publish this data, some of the agreement among the pathologists are very good. But look at those. There are sometimes a kappa value of minus. What does those mean? Interesting. And so actually, there still are quite a inter-observable variability for some of the diseases, such as interstitial lung disease. Then what's going to be the ground truth is quite a question. It's not only from our data. There are several other people looking at the similar things, and this is another paper. I went to the HSP and indicating about the similar very low kappa value among the pathologists. So, like a field like this one, it's like a somewhat look like a mess to some of the pathologists. How do we really, create a good model? Yeah, so like this one, the previously it was like a clinician asked the pathologist A and a pathologist B, and they were stuck, they were in trouble, by those answers. But then now it's us pathologists, we're having a problem by having a different answer from the different AI. So why does this agreement occurs? Okay, there are several different criteria, of course, exist, right? So some people said the disease like a UIP, okay, A is a UIP. It is widely, covered. Or some people say, no, no, it's a C is a UIP. And some people say, no, 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 it's limited to here. So A and B and C overlapping somehow, but they're not saying the exact right things. But what happened is when they, let's say, when they put the curve, each of all curves, survival curve, show the separation between the UIP and non-UIP. Then we are stuck, Oh wow, we cannot tell which one is right. But this happens sometimes. Um, we actually did one of the study, and which now we are publishing this paper. Uh, what we did was just uh, ask the pathologists, many 18 pathologists to sort out the images to those 8 categories. And how did we did it? How did we do? Is that we had cut these images into the patches and send them to the 18 pathologists of worldwide known lung pathologists. And then we create a smartphone app and ask them to select which one is this. So this looks like a UIP. Normal. Okay. Non-UIP connective tissue, no UIP. All right, something like this. So it's quite interesting work, and some of the cases are, how to say, having like a map like this one, and many areas are UIP, and some areas are mixture with NSIP. And based on those, we really want to classify the disease. So this is the raw data we got from the 1,100 images by the 18 pathologists. These are the images for each case. And then those numbers we collapsed into the one number for each case and did this, the survival, did the cluster analysis based on the diagnosis. Then we reached to have 3 different clusters. And each cluster has some features. Cluster 2 is having a more UIP. Cluster 1 is almost like half. And the cluster 3 doesn't have much UIP, actually 0 in the consensus. So interestingly, we plot the survival curve, and the cluster 1 only shows the separation of the survival. So that's why we concluded that the diagnosis from the cluster 1 is at this point ideal to create the model. So we set that as a ground truth and create the deep learning model. And this has a deep learning model of those 3 filters, a UIP, non-UIP, and normal lung, and made a classification model on top of it by using those data. And then we plot the survival curve, which predicted very nice survival predictions. So it's a way to go. Okay, then some people say, well, yeah, that's interstitial lung disease, interstitial pneumonia, that's difficult case, disease. And well, but for the cancer, the things are different. Yes, of course. Cancer versus non-cancer, we are not allowed to make mistakes, but that's not the case if you look at the one by one patches. So this is the data, the research done by our fellow at Chris. We also cut this into the patches and make once again the same smartphone app to ask the 18 pathologists, that's a different pathologist actually, more focused on lung cancer to sort out those images. And these are the raw data. As you can imagine, we have a trouble, between the Achner and non-invasive, lipidics and papillary versus Achner, those things. So this is one of the example for one particular case. This particular lung cancer case is these 18 pathologists, scored very differently. Some of the pathologists are more favored for the non-invasive tumor, and it's pretty close to the minimal invasive adenocarcinoma. But these pathologists favor papillary adenocarcinoma or fully invasive cancer. So those pathologists favor the Achner, predominant the adenocarcinoma. And this was actually this pathologist called this as more like a micropapillary adenocarcinoma. So these are actually the variability that we have among even an expert of the lung pathology. And then we also did the same approach to did that cluster analysis to separate those the pathologists into the groups, and we get 3 clusters. But because of this small number of the cases, we cannot reach to the survival separation or anything. So we ended up to create those 3 models based on those 3 data, and then comparing the deep learning answer by doing this survival analysis based on those models. So right now we are now testing those the models. So finally, I will touch a little bit about the explainable AI models. What is explainable AI models? We sometimes say XAI, not like explainable, XAI. This is similar to the, this is actually the occasion. If we use those AI in a daily practice, of course, we sometimes rely too much on the classification of the AI. But of course, AI can make mistakes as we do, based on the various reasons. But you cannot tell, well, it was AI and it's not me, to the patient, right? So we really need to have a very good explanation from the AI to really trust that. But there's the same thing about the pathologist diagnosis. So if you send some of the difficult cases to the expert consultation, so if you get a report like this one, okay, adenocarcinoma invasive, period, and signature, can you trust this? Okay, let's assume that this is quite a nice, brilliant pathologist. Can you just, simply trust this report? Or do you, you're probably not so far and happy, right? But if you have this one, have a nice pictures of why this was considered as, the adenocarcinoma, and those are the features they extracted, these are data to support, then we said, okay, well, this is the perfect report to really send back to the clinician. So it's the same things. We really need this type of explanation from the AI. So why do we need an explainability? You need to understand why AI concluded to the diagnosis before using it, and explainable models also advanced human-machine collaboration. And AI may be biased by the creators. So we, when we feel like, okay, we have a different answer from the AI, we have to compare that to our own result and also AI diagnosis. And for that, we definitely need why AI ended up to reach to the diagnosis. And explainable model make it easier for the medical professional, of course, to utilize AI in clinical workflow. There's no doubt about it. So I'll show you that what is the explainable AI. There are several the models. Many of the models focused on the explainability in this way. So one of the examples was called line. So how they do it? Okay, if you create the model to say carcinoma, and this the image was when this one image was analyzed, it says AI said carcinoma, which is right? So okay, correct. But if you hide this area, and then if the machine said, well, it's not cancer anymore, that's correct as well. So by that, we know that this machine is actually making judgment by the area of the cancer. Instead, if we mask this area, and if the number drops, we have to tell, whoa, wait. It doesn't have any relationship with cancer. So that's dangerous, something like that. Okay, so this AI model is not really looking at a cancer cell, looking at something else, but by accident reach the correct answer, something like that. So that's a line. The another one, which is more popular, is called GrandCam. So GrandCam is one of the model that, okay, so let's make a judgment of the dog or cat. And then we have a model. So, but when the machine make mistakes, how they learn is about not from the correct answer. They learn stuff from the mistakes. It's like us, same thing. So when machine made mistakes, what happened is that they just go back, the back propagation. So it was called back propagation, and go back to modify those numbers, formulas, kernels, as I said some minutes ago. And then there's some gradient occurs, right? And when the gradient is big, they consider that as an important area to really change the diagnosis. And then make a heat map of those high gradient area to put that in overlay to the images. So this is what they called GradCam. It's a similar to the line that they just indicate the area that where they make a judgment, the type of things. Another thing, what we favor more and we are trying to create in our laboratory is something different. It's one of the popular ways is extracting future, extracting explainable features using deep learning. So how do we do that? Is that we just use a similar deep learning model, and not to instead of going to the diagnosis, we just remove all of the last part of the formulas, layers, and using those feature map to group in several different ways, like a cluster analysis. So this is like a cluster analysis, one of the most common one as k-means. And then by doing so, we could separate images into the different groups. And by looking at those, we can tell, oh, okay, this cluster is more like a normal rank. This cluster is more like a, not meaning red blood cell, something like that. One of the example is that the prediction of survival in malignant mesothelioma. This is not our group. This is a group of the Francois Gattosali, and it says published in Nature Medicine. Oops, sorry, just there's a previous recording which I did in Japanese. Wait a minute, there are several recordings I forgot to remove. Okay, yeah. So what is good about is that they create the model to predict the survival, and there are high risk group, and the intermediate, and also low survival group. So they separate mesothelioma into these three groups. And what is interesting and unique about this paper is that they also show those images which is in the group of those high survival tiles and low survival groups. And this was one of the unique feature of this paper. Another thing is, oops, sorry, I thought I removed it, but it was not. Okay. Yeah, another thing was the model to extract the human intractable images in tumor cells. So this is more advanced. And here, as you can see, this model identifies 6 different features, like let's say epithelial cells, and each of the inflammatory cells, stromal cells, and the predict the mutations and type of things by those explainable the features. And this was published very recently in Nature Communications. And we also do the similar approach to the interstitial lung disease and reach to to extract the feature to really overlay on the pathology images and make a diagnosis. This is an unpublished here, so we cannot tell much in details. As you can see, we extract the feature. This is a case of the PPFE, which this model highlights the area of the elastosis, and we are more like feel reasonable and feel the okay highly confident to make a report of PPFE by looking at this the explainable AI. And what is good about it is this model predicted the diagnosis in a very high accurate manner and predicted survival. And so by doing this, what we are doing next is that we are now creating those UI, user interface, to implement this model to the clinic, and then try to highlight this, implement the better the report system to the clinic. So these were my talk and pretty much everything. But by using this opportunity, I want to introduce our society, Japanese Society of Digital Pathology, which will be held in actually this year, August 20th to 22nd. We have many wonderful the guest speakers, and it's all online, so you can join. Which is good about the online is that you can also join to this the session. And if you have some the abstract to submit, this is a deadline. Please join access to this address, and please join to our society meetings. So summary. We have developed a cloud diagnosis system, a consultation portal, MDD discussion network for pulmonary diseases, and collaboration between AI and pathologists to report tumor severity for lung cancer has been used in practice. We also had introduced about the creation of AI can be used to standardize pathologists in terms of variability, and I talk about the importance of having the nice ground truths, explainable ground truths to reach the very good AI, and also explainable AI to extract the broad features of UIP has been developed, and we are aiming to use it in practice soon. So by this, I would like to thank you for paying attention to my talk, and I'm happy to accept the questions. Thank you very much. So I don't know how to accept the questions. Is there any sharing? Is it coming from the chat? Okay. Well, I was expecting to have some sharing of this session, and if it's not, then I may maybe stop and let everybody have a rest. Once again, I really want to thank you for the giving this opportunity to me. Oh, here, there's one question coming to me. Okay, have your techniques been applied to other cancer areas? Oh, yes. And well, other cancer, we are not using this because I'm a pretty much lung pathologist, so I'm sticking to the lung pathology. But yes, the people are welcome to collaborate with us, and then that we can in collaboration. You can use our models and stuff, and One of the area which we are now trying to create is some of the GU area, because one of my fellow are pretty much interested in the GU. So that's one thing, and also hemato area, but it's not really the started yet. And how you optimize the cutoff for AI model? That's a very good question. For depending on the model, if that's just a simple classifier, then that the cutoff model would be validated by the diagnosis, and then that we just define the cutoff line. Um, and also for the heat map, we can have like a two ways. Maybe we can have a cutoff line like a zero point 0.5 to just put positive, negative heat map. Right now we're using this, but you can also use the whole variation of the color based on the probability. And for that, you don't need to set up the cutoff line. uh, For the ROC, yes, for the ROC, cutoff line is actually set up, or where, what was actually that one? Here, so it was, yeah, it was the here, well, cutoff line, I I actually don't quite remember. I'm sorry. Yeah, sorry. That is the question that I cannot really give you the exact right answer. Any other questions? Okay, so seems like yeah. Okay, thank you very much. So I'll finish by D here, and once again, I really want to thank you for your paying attention. Thank you.